We've seen that shockwaves can occur in the inlets of scramjets, and that's our motivation for finding out what happens as the flow passes through shockwaves. But where else in gas dynamics are we likely to encounter shockwaves? That's the subject of this unit. In our scramjet model, we saw that our flow is processed in the inlet by 3 oblique shockwaves before it enters the combustion chamber. In the last videos, we saw how we can visualise shockwaves in a shock tunnel. This is the small model of the 3-shock inlet that we tested in the UQ Drummond shock tunnel. You can see the kink in the inlet that generates the first shockwave, and here's the cowl. Let's have a closer look at what happens through this inlet. This is a Schlieren photograph taken with the model in the tunnel visualising the flow through the inlet. We can see the first shockwave generated by the first compression surface of the inlet. The second shockwave we see being initiated near the change in shape halfway along the inlet. And the third shockwave is initiated by the cowl. You may have noticed that the third shockwave is visualised as a white line, but the first and second shocks are dark lines. Why is this? Well, it's because a horizontal knife edge was used for the Schlieren. And in this setup, any density gradient that is positive upwards leads to a dark region on the image, and any density gradient that is positive downwards leads to a light region. Let's look at the first shockwave. Let ρ be the density of the flow approaching the inlet. The density of the flow increases as it passes through the shockwave. So behind the shockwave, the density is larger. Therefore, the density between that first shockwave and the upper body of the scramjet is higher than it is upstream of the shockwave in the oncoming flow. I've used a larger symbol for ρ to indicate the higher density there. So the density gradient is positive upwards, and we see a dark line where the shockwave is located. The same sort of thing happens across the second shockwave. The density downstream of the second shockwave is larger than the density behind the first shockwave, indicated again by a larger symbol for ρ. So again, the density gradient is positive in the vertical direction, and the shockwave appears as a dark line in the Schlieren photograph. The third shockwave, the shock generated by the cowl, increases the density further again. But this third shockwave is inclined upwards, so the density below the shockwave is higher than the density above the shock. So the density gradient is positive in the downwards direction, and we see a white line where the shock is located. Let's look at where some other shockwaves occur. This is a photograph of the SR-71 Blackbird taking off. We can see some bright spots in the exhaust of the engine. The bright spots are referred to as shock diamonds. The flow exiting the engine is supersonic, and if the pressure at the exit of the engine is either lower or higher than the air into which the exhaust is flowing, we can get a series of normal and oblique shockwaves occurring in the exhaust. The pressure and temperature of the exhaust gases increase as the flow passes through the normal shockwaves, so the gas is hot in those regions. This can cause any excess fuel to burn and glow, or the gas can just get so hot that it starts to glow. Here is another example of where a flow gets so hot as it passes through a shockwave that we can see where the shockwave occurs. This is a photograph of a pitot probe in the X2 expansion tunnel at UQ. Here's one of these probes. We use them to measure the pressure in the flow so that we can quantify the flow conditions generated in the tunnel. The X2 tunnel is capable of generating flow speeds in excess of Earth orbital speeds for up to a few hundred microseconds. This type of photo is referred to as a luminosity photograph because the flow luminesces in regions of very high temperature. The flow here is hypersonic, and a bow shockwave forms and wraps around the probe. Right on the axis of the probe, the bow wave is at 90 degrees to the oncoming flow. So the shockwave right at that point is a normal shockwave. The flow on the streamline passing through the normal shockwave is not deflected as it passes through the shock, and the flow Mach number drops from hypersonic upstream to subsonic downstream of the shock. The temperature of the gas gets up to thousands of degrees Celsius immediately behind the normal shockwave. Any impurities in the gas then luminesce, showing up as bright white regions in the photo. We see that the shockwave off the axis is curved. The shockwave is no longer a normal shockwave, and it gets weaker as we move away from the axis. If we look at what happens to the flow as it passes through the shockwave away from the axis, we'd see that the flow would be deflected upwards behind the shockwave. So at this point, we have an oblique shockwave, much like the shockwaves on the inlet of our scramjet model. However, as I pointed out when we were looking at curved shockwaves in the introduction to this section, the flow is not uniform behind the shock, and the streamlines downstream of the shockwave will be curved. I said in the introduction that it's unusual for us to be able to see shockwaves with the naked eye, or in this case, with a normal camera. We needed a camera to be able to see the shockwave here because the flow is of such short duration in an expansion tunnel that everything would be over in less time than the blink of an eye. The rest of the shockwaves we'll see in this unit are visualised using the type of techniques that David and Nassim showed in the video on the Schlieren technique. Here is a Schlieren photograph of a Northrop T-38 Talon aircraft flying at Mach 1.1. It was taken by NASA Langley's Dr. Leonard Weinstein using a Schlieren technique he developed to visualise the shockwaves around aircraft in flight. The T-38 is flying from right to left here. At a flight Mach number of 1.1, it is flying right in the transonic regime. The Schlieren effect allows us to see shockwaves being generated by different parts of the aircraft. Because the Mach number of the aircraft is so close to 1, the shocks are close to being normal shockwaves. As the waves propagate further from the aircraft, they become weaker as regions of expansion of the flow catch up with the shockwaves and weaken them. Shockwaves can be generated when there's a sudden release of energy, such as by the explosion shown here. This shadowgraph, taken by Gary Settles from Penn State, shows the shockwave a short time after the detonation. What we see here is a spherical shockwave. The wave moves outwards from the centre of the explosion at the same speed in all directions. This type of spherical shockwave propagates through the still air at a speed higher than the speed of sound. The compression of the gas as the shockwave passes is followed by an expansion, which we can't see clearly here, taking the gas back towards its original pressure and temperature after the wave has passed. The wave weakens as it propagates away. We can approximate the wave as a normal shock wave at large distances from the explosion. The last photograph of a shockwave that I want to show here was also taken by Gary Settles. This shows a shadowgraph of a bullet being fired from a rifle. Again, here we can see a spherical shockwave. This is generated by the high pressure gases leaving the rifle after they've pushed the bullet out of the rifle. And we can see the bullet moving away to the left. This bullet is moving supersonically, and we can see a series of oblique shock waves being generated by the bullet. These are just like the oblique shockwaves we saw in Ernst Mach's photograph in the introductory section of the course. So shockwaves can occur in a range of situations. In all cases, they have to be regions of supersonic flow, or regions where shockwaves propagate at supersonic speeds relative to the gas through which they're moving. We're going to start our shockwave analysis by considering the simplest case, the normal shockwave, in the next unit.